So in my last video I forget to tell one thing which I happened to see in PhD defense of a guy. They asked about the NMR spectrum to that guy. They asked, actually, look, uh, there's ethylene here, and we have acetylene here. And look, in NMR spectroscopy, this thing is going to give around 5 to 6 ppm, but this thing is going to give around 2 to 3 ppm, but the benzene is going to give around 7 ppm, like that. And usually in NMR the sp3 will have a less and sp2 and lesser than sp. The chemical shifts is going to have this kind of trend there. It's explained because look, the electron is very close to the nucleus here, to the carbon nucleus. Therefore H will have a it's highly de-shielded. Therefore we have a split, we have a shift in the higher range like 5 and 6 or like that. But you see here in this case, you see, even though this is an SP, but we get very very less 2 to 3 ppm. In that PhD defense, the persons asked this question to that guy, and he didn't said it, and he should have told it. I know, actually I also don't, I know there's a thing called magnetic anisotropy. This phenomenon is because it's because of the magnetic anisotropy. It's because, see, I already told you in my last video that a spin, NMR is due to the spin of the nucleus, and it's going to affect by the nucleus of the nucleus neighboring the target nucleus. Also, the nucleus spin is also affected by the electrons around the nucleus. Electrons are also charged particles. When they move, they also produce a magnetic field, and that magnetic field is going to affect. It's going to shield the applied magnetic field we apply during the NMR analysis. Therefore, in benzene we have a ring current there. A ring current is there, and it's going to repel the applied magnetic field. But fortunately, the electrons are out of this ring current. Therefore, it's going to be highly de-shielded because of the sp nature. The ring current is not shielding the electrons. The protons are not shielded by the ring current. Therefore, the applied magnetic field will have a greater effect on this benzene H. But if you take this, if you draw acetylene in this weird way, we have a magnetic field like this, and unfortunately the H's are in the line of this electron cloud, and it's going to be shielded by this applied magnetic field. Therefore, we will not have any the hydrogens are shielded by the inherent inherent field we have here. Therefore, they don't process that much. Therefore, they'll need a higher frequency to process, higher radio frequency. That's why it's near DTMS, or it have a very very low chemical shift there. The hydrogen stuck in the electronic cloud there, that electronic cloud which repels the applied magnetic field. Therefore, the applied magnetic field will have a lesser effect on this hydrogen, but here the case is different. That's why we have this kind of difference. And yeah, it's a good thing. I thought in PhD defense they're gonna ask me some really hard stuff, but it's a very basic stuff they asked. Therefore, it's good. Now, as I'm working, I don't get any chance to see any PhD defense, But those who are still in college or doing research in any institution, they will have a lot of, they will able to see a lot of PhD students, and it's going to be fun, I guess. That's the thing I miss from the college days. You can always see other people work, you can get inspiration and stuff and all. In work also I get different sort of inspiration, but not of this kind.